A 400 amp meter section is still required even without a breaker or disconnect because of National Electrical Code section 695.3. This section states that a single source must be capable of supplying locked rotor current indefinitely. The locked rotor current of the motor is 257 amps, necessitating a meter section rated for at least that amount. The number 6 conductors are not the weakest link in the chain. The motor itself is actually the weakest link. It's rated for 15 horsepower, limiting the amount of current it can handle. Exceeding this rating will cause the motor to overheat and burn out. A 200 amp meter isn't adequate for protecting the motor. If the current exceeds 200 amps, the meter will trip, leaving the motor unprotected. Therefore, a 400 amp meter section is necessary to properly protect the motor. Let's delve deeper into the reasons why this is the case. Firstly, fire pumps are considered essential equipment in a building's fire protection system. Their reliable operation during a fire is paramount. Secondly, the National Electrical Code has specific requirements for fire pump installations to ensure this reliability. Section 695 is dedicated to fire pumps, covering aspects from power sources to wiring methods and protection devices. A key requirement is that the fire pump must have a reliable power source capable of supplying the necessary current, even under locked rotor conditions. Locked rotor current, or LRC, is the current drawn by a motor when it's initially started and the rotor is not yet turning. This current can be significantly higher, often several times the motor's full load amperage or FLA. In this case, the motor has a full load amperage of 46.2 amps, but a locked rotor current of 257 amps. This high inrush current places a considerable strain on the electrical system. Section 695.3 of the NEC mandates that the power source be capable of supplying this locked rotor current indefinitely. This is because the fire pump may need to operate for extended periods during a fire. The intent of this requirement is to prevent the power source from being overloaded or failing during a critical emergency. The meter section, which is the point where the electrical service enters the building and is metered by the utility company, must be sized appropriately to handle this locked rotor current. Even if there is no overcurrent protection device, such as a breaker or fuses, immediately ahead of the fire pump controller, the meter section must still be sized to accommodate the locked rotor current. This is because the meter section is part of the overall power source and must be capable of meeting the requirements of NEC 695.3. The argument that number 6 conductors are the weakest link and will melt down before the 200 amp meter is not a valid justification for using a smaller meter section. While it's true that conductors have ampacity ratings, meaning they can only safely carry a certain amount of current, relying on them to act as an overcurrent protection device is not code compliant or safe. Conductors are designed to carry the load, not to intentionally overheat and fail. Overheating conductors can create a fire hazard and should be avoided. The purpose of overcurrent protection devices, such as breakers and fuses, is to protect the conductors and equipment from overloads and short circuits. These devices are designed to trip or open the circuit when the current exceeds a safe level, preventing damage to the system. In the absence of a breaker or fuses immediately ahead of the fire pump controller, the overcurrent protection devices upstream, such as at the main service panel, are relied upon to provide this protection. However, these devices must still be sized appropriately to allow the fire pump to start and run under locked rotor conditions without tripping. This is where the 400 amp meter section comes into play. It provides the necessary capacity to handle the locked rotor current without causing the upstream overcurrent protection devices to trip. It's important to note that the size of the meter section is not solely determined by the locked rotor current. Other factors, such as the overall electrical load of the building and the potential for future expansion, may also need to be considered. However, in the case of a fire pump, the locked rotor current is a critical factor that must be taken into account. The statement that the 200 amp meter is not large enough to protect the motor is correct. While the meter itself may not directly protect the motor in the same way that an overcurrent protection device does, its capacity is essential for ensuring that the motor receives the necessary current without causing the system to be overloaded. A 200 amp meter would likely be undersized for a fire pump with a locked rotor current of 257 amps. This means that the meter could be overloaded during motor starting, potentially leading to voltage drops and other problems that could affect the fire pump's performance. Furthermore, an undersized meter could also limit the amount of current available to other loads in the building. In summary, the requirement for a 400 amp meter section for a 15 horsepower fire pump with a full load amperage of 46.2 amps and a locked rotor current of 257 amps is based on NEC 695.3, which mandates that the power source be capable of supplying locked rotor current indefinitely. This requirement applies even if there is no breaker or disconnect immediately ahead of the fire pump controller. The 400 amp meter section provides the necessary capacity to handle the locked rotor current without overloading the system or causing upstream overcurrent protection devices to trip. Relying on number 6 conductors to act as an overcurrent protection device is not code compliant or safe. Overcurrent protection devices are designed to protect conductors and equipment from overloads and short circuits. While the size of the meter section is not solely determined by the locked rotor current, it is a critical factor that must be taken into account to ensure the reliable operation of the fire pump during an emergency. The fact that the motor is rated for 15 horsepower is relevant because it dictates the motor's full load amperage and locked rotor current. A larger motor would typically have a higher full load amperage and locked rotor current, requiring a larger meter section. The choice of number 6 conductors may or may not be appropriate depending on the specific installation and the ampacity ratings of the conductors. However, the conductors must be sized to carry the full load amperage of the motor, plus any applicable dirting factors. The overcurrent protection devices upstream, such as at the main service panel, must be sized to protect the conductors and equipment from overloads and short circuits. These devices must also be sized to allow the fire pump to start and run under locked rotor conditions without tripping. The size of the meter section is just one component of the overall electrical system designed for a fire pump installation. It's important to consult with a qualified electrical engineer or contractor to ensure that the system is designed and installed in accordance with all applicable codes and standards. Proper installation is essential for ensuring the reliable operation of the fire pump during an emergency, protecting lives and property. The size of the meter section directly relates to the locked rotor amps because the meter section must be sized to accommodate the inrush current that occurs when the motor starts. This inrush current, also known as the locked rotor current, can be several times higher than the motor's normal running current. If the meter section is not sized large enough to handle this inrush current, it can cause the voltage to drop, which can damage the motor and other equipment. It can also cause the overcurrent protection devices to trip, shutting down the fire pump. The NEC requires that the meter section be sized to at least 125% of the motor's full load amps plus the locked rotor amps. This ensures that the meter section is large enough to handle the inrush current without causing any problems. In the example given, the motor has a full load amperage of 46.2 amps and a locked rotor current of 257 amps. Therefore, the minimum size of the meter section would be 1.25 times 46.2 amps plus 257 amps, which equals approximately 315 amps. Therefore, a 400 amp meter section is required. The 400 amp meter section is needed to handle the fire pump's locked rotor current indefinitely because the fire pump may need to run for an extended period of time during a fire. The locked rotor current is the amount of current that the motor draws when it is first started. This current is much higher than the motor's normal running current. If the meter section is not sized large enough to handle the locked rotor current, it can cause the meter to overheat and fail. It can also cause the voltage to drop, which can damage the motor and other equipment. The NEC requires that the meter section be sized to at least 125% of the motor's full load amps plus the locked rotor amps. This ensures that the meter section is large enough to handle the locked rotor current indefinitely. The motor's horsepower rating is also relevant to the size of the meter section. A larger motor will have a higher full load amperage and locked rotor current, which will require a larger meter section. The NEC provides tables that can be used to determine the minimum size of the meter section based on the motor's horsepower rating and full load amperage. The type of conductors used to connect the fire pump to the meter section is also important. The conductors must be sized large enough to carry the motor's full load amperage and locked rotor current. The NEC provides tables that can be used to determine the minimum size of the conductors based on the motor's amperage and the type of insulation used on the conductors. The overcurrent protection devices, such as circuit breakers or fuses, must also be sized properly to protect the motor and conductors from overloads and short circuits. The NEC provides guidelines for sizing overcurrent protection devices based on the motor's full load amperage and locked rotor current. It is important to note that the NEC is a minimum standard. It is always a good idea to consult with a qualified electrical engineer to ensure that the electrical system is designed and installed safely and correctly. A qualified electrical engineer can take into account all of the relevant factors, such as the motor's horsepower rating, full load amperage, locked rotor current, conductor size, and overcurrent protection device size, to ensure that the electrical system is properly sized and protected. Furthermore, the type of fire pump controller being utilized can influence the design. Different types of controllers may have varying inrush current characteristics, impacting the required meter section size. Solid-state controllers, for instance, might offer reduced inrush current compared to across-the-line starters, potentially affecting the overall system requirements. Careful consideration must also be given to the coordination of overcurrent protection devices. Selective coordination ensures that only the overcurrent device closest to the fault will trip, minimizing disruption to other essential loads. In fire pump systems, this is crucial to maintain power to the pump during a fire event. Coordination studies are typically performed to determine the appropriate settings for each overcurrent device in the system. Also, voltage drop calculations should be performed to ensure that the voltage at the motor terminals remains within acceptable limits during motor starting. Excessive voltage drop can prevent the motor from starting properly or cause it to overheat. Factors such as conductor length, conductor size, and the motor's locked rotor current all contribute to voltage drop. In addition, the presence of other loads on the same electrical system can also affect the voltage drop experienced by the fire pump motor. If the voltage drop is excessive, it may be necessary to increase the conductor size or use a higher voltage service to ensure proper motor operation. The ambient temperature in which the electrical equipment is installed can also affect its performance. Higher ambient temperatures can reduce the ampacity of conductors and the ratings of overcurrent protection devices. Therefore, it is important to consider the ambient temperature when selecting electrical equipment for a fire pump installation. The NEC provides rating factors that can be used to adjust the ampacity of conductors and the ratings of overcurrent protection devices for different ambient temperatures. Finally, the local utility company's requirements may also need to be considered when designing a fire pump electrical system. Some utility companies may have specific requirements for fire pump installations, such as the type of metering equipment that must be used or the location of the service disconnect. It is important to contact the local utility company to determine their specific requirements before beginning any work on a fire pump electrical system. Always prioritize safety and compliance with all applicable codes and standards. Working with electricity can be dangerous, and it is essential to take precautions to protect yourself from electric shock and other hazards. If you are not qualified to work on electrical equipment, it is best to hire a qualified electrician to do the work for you.